Okay, so for our initial discussion of streams, we're going to have a very simple example. Let me call this project streams. So this example is going to be an example of using a single stream and just queuing up operations on it. So as always, going to get rid of pretty much everything that's in here and add a few headers to the top. So what are we going to use? We're going to use IOStream as always. We're going to use CMath. I'll show you why in a sec. I'm going to use CTime as well and get the namespace in here. Okay, so what we're going to do is we're going to let me define the kernel first of all, so you see what's going on. Global void kernel. So I will have inputs A and B and an output C. And well, let's get the thread ID. Assume that both the blocks and the threads are flat, so one dimensional. So that would be block dimension dot x times block index.x plus thread index.x. And then I'm going to do c at tid equals, well, let's do error function, ERFF of a at tid plus b at tid. I just want something that takes some time to actually calculate. All right, so we're going to do this on a rather large number of entries. So let's do const int total count equals, and we're going to split this total count. So we're going to split the total number of entries into several smaller invocations. So shall we say? So there's going to be several chunks of elements. So let's have const int chunk count first of all. So the number of elements in the chunk count, let's say 2 to the 20, and then the total count will be chunk count times 8. There we go. Okay, so in this case, what we have to do, and apart from avoiding silly mistakes, what we have to do is limit the thread ID. So thread ID has to be less than chunk count. So we're going to call the kernel with chunks of data rather than the total amount of data. Okay, so this is my kernel. This isn't something that's going to change in any way throughout the examples. Let's now do a kernel call that's going to use a stream to actually queue up different chunks for this kernel to call. So int main. Right. So what do we want to do? Well, at this point, you might want to actually check whether your device supports overlapping. But you can go to Nsight Windows System Info. It's probably the simplest way if you're sure that it's going to happen on this device. And then here you can look at GPU overlap. So in my case, it's a 1, so I'm safe. But I mean, just in case you wanted to sort of find out whether or not it's supported, you'd write something like this. So CUDA device prop in device, you would say CUDA get device. I'm going to make the assumption that there's only one device here. CUDA get device properties. So get the properties for the device. And then you want to check prop device overlap. So if that fails, then just return or complain, whatever. So that's how you would do such a check. I'm going to assume that we have it just about everywhere. All right. So let's talk about what we want to do. We're actually going to use events as well to record the whole thing. So let's get those into place. So CUDA event _t start and end, and then CUDA event create the start event, create the end event as well. All right, and then we're going to create a stream. So we're going to have just one stream, but we're going to be queuing up lots of things on that stream. So CUDA stream _t stream, then use CUDA stream create to actually create that stream. Like so. Okay, we're done. So what do we want to do now? Well, now we want to actually allocate A, B, and C on both the host and the device. So you've seen this before, like a zillion times. Float, HA, HB, HC, DA, DB, and DC. And then we're going to, well, we need to calculate a few things. So the total size of the data is total count times size of float, and then const int chunk size equals chunk count times size of float again. All right. And then we can actually allocate memory. So we can say CUDA malloc DA, that's chunk size. So for the CUDA side, we allocate only the chunk size. Let me duplicate this for DB and DC. And for the host side, that's where we have to allocate the whole thing. But we're not going to use the CUDA. We're not going to use new or malloc or whatever. We're going to use that page locked function. So CUDA host alloc. That's what we want to use. And we provide a pointer to HA. We say total size. So we allocate all the elements, not just for one chunk. And then we do CUDA host alloc default. There are a couple of different options here, but I'm not going to discuss them because they're a bit more advanced. So replicate this once again. Let's HA, HB, HC, like so. And now let's actually fill up A and B with some noise. So I'm going to use, so remember previously when we filled up variables with noise, we did it using curand, which actually did it on the GPU side. Now I want to do it on the CPU side. So I'm going to use srand unsigned time 0. And for I going from 0 to total count, I'm just going to say that HA at I is going to be, let's just do rand divided by rand max. So roughly, numbers will be roughly from 0 to 1. It doesn't matter at all for this demo what they actually are. I don't think it changes the performance that much, although it might because we're doing an error function. Anyways, we get HA and HB initialized. So what we could do now is we can actually start, recording our events. So CUDA event record. So that's the start event, and it's going to be on the stream that we're using. So now we are in fact leveraging this stream parameter. Okay, so what we're going to do is we're going to go through a counter jumping over each chunk of data, and we're going to take each chunk of data and just send it to the kernel, and then we kind of sum up what all the invocations are. So let's do a for loop that's going from 0 to total count. But it's actually going to be incremented not by 1, but by chunk count, because we're jumping over chunk amounts each time. All right, so what are we doing here? Well, we're using this new call, CUDA memcpy async. So this is something that instead of just copying data straight away, it kind of queues it up for the stream to actually do it. When that happens, well, at some point it will happen, but we don't know where. So we copy from HA plus I is our jump size, shall we say. We copy chunk size, and here we do CUDA memcpy host to device, and let me get rid of the Solution Explorer, and the last parameter is conveniently that stream that we're interested in. So that's what we're doing for A. Let's do the same for B. Just change the values here. All right, so we copy the data over, and then we call the kernel. So let's do them in groups of 64 threads. So that would be chunk count divided by 64. We're not using any shared memory, so this parameter is 0. And here comes the fourth parameter to the kernel. Once again, that's the stream that we're going to use. And we pass DA, DB, and DC, predictably enough. Almost looks like a typical kernel invocation that we've actually used before. All right, and then once we've got the data, we do CUDA memcpy async again. Only this time we copy to HC plus I, and we copy from DC once again, chunk size, and CUDA memcpy, this time device to host, and once again providing the stream there. All right, so that's what's happening in this loop. And now we probably want to stop timing it and actually get our values. So let's do that. But first, we make sure that we actually wait for the stream to finish all the operations. So we say CUDA stream synchronize, and synchronize on this stream, the only one that we have. And then we do CUDA event record for the end event at the stream again, and CUDA event synchronize end. And then we can calculate how much time it actually took. So we say float elapsed, and then we do CUDA event elapsed time. So how much time did it take? Pointer to elapsed, start, end. There we go. And then we say, we can actually see out it now. This took elapsed milliseconds. There we go. And unfortunately, yes, we do need to do some cleanup. And instead of delete or whatever, we have to use a special function once again for the pin memory. So CUDA free host HA, copy it a couple of times for B and C. For the device memory, it's as always CUDA free DADBDC, and destroy the stream as well. So CUDA destroy stream. Oh, destroy stream. Wipe out the stream, and then just pause here. Get char. Right. Let's try and figure out why it's complaining about. Oh, of course, it's CUDA stream destroy, not destroy stream. There we go. All right, so this is good to go. We can actually try running it now. All right, so looking at this, it took us 87 milliseconds. So let's close this, and I'm going to actually note this value. So 87 milliseconds.